Okay, after our deep dive into the polynomial ring, we're going to go back a little bit and we're going to just try to do a broad strokes overview of some common places where we have arithmetic. So arithmetic just means we can add and multiply. So I just copied this directly from our book. Let me just be clear about what these sets are. That's n, that's a z, that's the even integers, that's a rational number, that's polynomials where we have rational coefficients instead of integral coefficients. That's z8, that's z2, that's R, that's C, and this is 2 by 2 matrices over R. So let's go through and check all the properties, and maybe let's go row-wise to see the difference. So in each of these cases, when you take two elements, if you add them, is it still an element there? Well, yeah, if I add two numbers bigger than or equal to 1, they stay bigger than 1. If we add two integers, we get an integer. If we add two even integers, it's still an even integer. If we add two rationals, it's still a rational. If we add two polynomials with instead rational coefficients, so it works the same as integral coefficients, but instead we have rational numbers. Do we still get a polynomial with rational coefficients? Yeah. Is addition closed in Z mod 8? Yeah, that was the content of chapter 1. Is it closed in Z mod 2? Yeah. Is it closed in R? Yeah. Is it closed in C? Yeah. Addition of matrices is entry-wise, right? So A, B, C, D, A1, B1, C1, D1, plus A2, B2, C2, D2 is A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2. Do we again get a 2 by 2 matrix? Yeah. Okay, great. Nailed it. What about times? If I multiply two natural numbers, we again get a natural number. Same with integers, same with even numbers, same with rationals, same with polynomials with rational coefficients, same with Z mod 8, same with Z mod 2, same with R, same with C, same with 2 by 2 matrices. These first two rows is just saying that we can do arithmetic. There's a plus and there's a dot. So we have some arithmetic operations. Now we're going to check, do they behave like normal arithmetic? So is plus associative in n? Yep. Z, yep. 2z, yep. Q, yep. Q join x, yep. Z mod 8, yep. Z mod 2, yep. R, yep. C, yep. Matrices are entry-wise, and it's just a bunch of additions in R, so it's defined like by doing 4 separate additions of real numbers. So it's associative for real numbers, so it's going to be associative there as well. Is times associative? Yep. Is in Z? Yep. 2Z? Yep. Q? Yep. Q join X? Yep. Although we didn't prove it because it's a little bit involved, but it is. Z mod 8? Yep. Z mod 2? Yep. R? Yeah. C? Yeah. Matrices? Yeah. Is plus commutative? Well, yes, 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 yes. Is times commutative? Yes, 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 no. Right? If you pick two random 2 by 2 matrices, the probability of the computing their product one way and the other way is and getting a different answer is very, very high. So matrix multiplication is not commutative. Plus times distributes over plus. Yep, 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 yep. There is an additive identity. Yep, 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 yep. All elements have additive inverses. Yep, 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 yep. There's a lot of greens here. It's because arithmetic is ubiquitous, is why there's a lot of greens here. There's a multiplicative identity. Yes, yes, no. The multiplicative identity should be 1, but we're in even integer land. So no. And then we have yes, 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 and then the identity matrix, of course. All non-zero elements have multiplicative inverses. No, 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 yes, because Q is a field. No, oops, it's the wrong color. Why no for Q adjoin X? Well, the same reason why it was no for Z adjoin X. Absolutely the same reason. If your polynomial has positive degree, You can only increase the degree by multiplying by something, or the degree at worst, at best, stays the same. Z mod 8, no. 2, for example, has no multiplicative inverse. Z mod 2, yeah, Z mod 2 is a field because P2 is prime. R, yeah, R is a field. C, yeah, C is a field. Matrices, no. No in matrices. You only have a multiplicative inverse when the determinant's non-zero. And a lot of matrices have a zero determinant. All right, so what is this trying to say for us? Well, it's trying to say that if we want to think more broadly about doing arithmetic and other number systems, we're going to have to relax some of our field axioms. Right? So in particular, we're definitely going to have to throw out the existence of multiplicative inverses. And it feels morally wrong to me to not have a multiplicative identity, but your book and when you start out, it's good to keep your mind open for other types of number systems. So we're actually going to even relax having a multiplicative identity, so we can think about things like 2z. And we also want to think about guys like 2 by 2 matrices or n by n matrices. And so we're also going to need to relax commutativity. So these are the three axioms that we're going to delete from the field list in order to define a ring.